Hi there, and welcome back to Chapter 2.3 from Stevens' Matrices, Vectors, and 3D Math. This is the second video from this chapter where we are discussing the dot product. And the first video discussed the definition of the dot product, how we can use the dot product to do a lot of trig without using any of the trigonometric functions. And it basically came from the second definition for the dot product, u dot v, is the size of u times the size of v times the cosine of the angle between the two vectors. And if you solve that for cosine theta, we got the very handy cos theta equals u dot v over size u times size v. Alright, we were able to tell whether angles were the angles between the vectors were right angles, obtuse, acute, whether two vectors were going in the same direction, in opposite directions. We were able to do a little trick on collision detection right back here of determining when this ball crossed a wall by determining whether the sign of the dot product between this vector and that vector changed. So all you had to do was take the dot product of these two vectors, and as soon as it changes sign, then this ball, the terminal point, crossed the wall. Very handy stuff. Now we're going to use the dot product to do projections, and we're going to be relying on that particular formula, which is just a rewrite of the definition of the dot product with the cosine in there. And so we're going to talk about projections, and the notation looks like this. This is called the projection of a vector u onto a vector v. And there's a formula for that, but we'll derive it actually. And so what I mean is if I have a vector v here, right, and then a vector u here, and I make it so they're original points, are on top of each other, then the projection of u onto v comes from dropping u perpendicular into the direction of v, and this is the projection of u onto v. Right? And you can go in either direction. Suppose that angle wasn't acute, suppose it was obtuse, then the projection of u onto v comes from dropping that perpendicular again, only now my projection of u onto v is going in the opposite direction of v. Right, so it does depend on the angle. So we're going to determine a formula for this, first using trig, but then we'll be able to eliminate all trig because we can do that with the dot product. Okay, so let's take a look at it. If we wanted to find this vector right here, and we have u and v and the angle between them, then the length of this, right, the length of this would be easy to get. That would just be the length of u times the cosine of this angle. Right, so that length is given right here. That's the proper length. Right, and it looks like it's in the right direction. The problem is it's just a single. It's a scalar. It's just a single number, right? I need to give it. It needs to be a vector, so it needs to be pointing in the proper direction. That proper direction is determined by v. So the unit vector in the direction of v is given by v over the size of v. So I get the length, multiply it by the vector, the unit vector in the correct direction, and that gives me the vector that I want. That gives me the projection of u onto v. Right? But now this has cosine, and I want to do this without any trig functions. So what I'm going to do is go back to this formula right here. Right? And I'm going to replace the cosine of theta with that term on the right. So there's the cosine of theta. I replace it with u dot v over sine u sine v. The u's cancel. The v's, size v, that's just size v squared. The u dot v stays. And then I multiply all that by the vector v. So the formula for the projection of u in the direction of v is given right here, and the thing to notice is that there's no trig. It's the beauty of the dot product right there. So we'll do a couple of examples here. The first in 2 space and the second in 3 space. Suppose I have 2 vectors from 2 space. I'm going to find the projection of u onto v, the projection of v onto u, and the projection of v onto negative u. All right. Okay, so projection of v onto u. I get the u dot v, so that's just negative 2 times 0 plus 2 times 3 is 6 over the size of v squared, so that's just going to be 0 squared plus 3 squared, which is 9. Take the square root, but then I'm squaring it, so I'm just left with the 9. Times v, right, which is right there. And when I do that, I get 0, 2. I perform the scalar multiplication, basically 6/9 times 0 and 6/9 times 3. And notice, this is important, the projection of u onto v is parallel to v. If I do the same thing when I project v onto u, I go through some similar math, the difference being that I'm dividing by the size of u squared and I'm multiplying by the vector u. And when I do that, get the length, get the direction, and then I'm going to do the scalar multiplication. I get negative 1.5, 1.5. Notice that is parallel to u. The projection of v onto u is parallel to u. So that's important, right? Whatever you're left with has to be parallel to what you're projecting on. That's what we mean by a projection. And then this last one is just meant to demonstrate a property of projections. Specifically, if I take the projection of v onto negative u instead of the projection of v onto u, what you'll notice is that they're the same. So I'm going to erase all this so that doesn't get in the way. So notice it looks like these two things look very much alike, except that here I have a negative u. That's going to be just a negative out in front. There's a negative in there, but that's squared, so that goes away. And a negative u right there. But the negative u for the vector and the negative u in the dot product, they're going to cancel each other out, and I wind up with the exact same thing. Right? So the projection of v onto negative u is the same thing as the projection of v onto u. Right? And so that should make sense. If this is v and this is u, right? This would be the projection of v onto u. Right? But then if I just take, instead of u, if I take negative u, the projection of v onto negative u, you still drop that 90 degree, and you wind up with the same thing. So these are not just algebraic properties to be memorized. They're actually, there's a geometric interpretation involved as well. So now if we go into 3 space, 2 vectors from 3 space, I'm going to find the projection of u onto v, v onto u, and then the projection of negative v onto u. And the formula is the same. There's just one extra multiplication and addition whenever I'm doing the dot product and magnitudes. So if I take u dot v, so first I'll do the projection of u onto v. By the way, it doesn't matter whether you're doing u onto v or v onto u. You're going to get that same dot product up top. So let's see, that's going to be negative 2 plus 0 plus 3 is 1 divided by the size of v squared. That's going to be 1 plus 0 plus 9 is 10 times v. All right. And when I do that, I get this vector here, and notice the projection of u onto v is parallel to v, as it should be by definition. If I switch things around and I project v onto u, the dot product up here stays the same, but now I'm dividing by the size of u squared instead, and I'm multiplying by u. So it does change, and I get this vector here. All right. And notice in this case, so I have negative 2/9, 2/9, 1/9. If you compare that to u, negative 2, 2, 1, it is actually parallel. I mean, and you can actually see it's got to be parallel, right? It's got to be parallel to u because it's actually just a scalar times u. Projection of v onto u is parallel to u. I guess the other important thing to notice, though, is that the projection of u onto v is not the same as the projection of v onto u. You can't switch their roles. They result in very different vectors. Finally, if instead of projecting v onto u, if we project negative v onto u, right, so instead of just v onto u, I'm doing negative v. The only place that v even shows up is right here. So it becomes a negative. Nothing else changes. So I actually have a negative out in front. And the projection of negative v onto u is the same as the projection of v onto u. The negative projection of v onto u. And that should make sense. All right. If this is v and this is u, then this here is the projection of v onto u, right? And then this is going to be the negative of that, negative projection of v onto u. But that's the same thing as taking negative v and projecting it onto u. I'll give you this exact same vector. All right, so again, it's more than just an algebraic property. It is, in fact, a geometric representation of projections as well. All right, so we're going to use this little projection formulas to do a little application. And again, this is an application in game programming where we have an object that is starting at m, and it wants to go to q via this velocity vector, but it hits a wall at the point p, and there's two things that can happen. You can get, say, a slide response, which is, maybe if that's a car hitting a wall or something, or you get a bounce response. All right, so we have the slide response if that's maybe a car or a character, or a bounce response if it is, say, a ball. All right. Okay, and so to get these different responses, the slide response is really quite easy. You do have to figure out what p is. But once you have pq, this vector, that's pq, all you have to do is project that onto the wall vector, and that gives you your slide vector. All right. So that's your slide. It's a pretty easy thing to get. It's a simple projection of what's left of your velocity vector down onto the wall. But now in order to get this final slide point, and that's what I call the slide point, I actually have to do a inconsistent addition. This is a point P, and this is the bounce vector S. Or sorry, not the bounce. That's the slide vector S. If I take this point and add it to this vector and treat it like a point, that will result in the final position of the ball or the character with a slide response. Now, if I want to get this bounce response, it's a little trickier. I'm going over here. I'm going to bounce. And we want our bounce vector here, which is imposing that these two angles, the incoming angle and the outgoing angle, are the same. And so the easiest way to get this bounce vector is to think about this slide vector first over here on the left. This slide vector is going to go right there, right? That was S. And so what I'm going to do is I'm going to go over from S like that. That's going to give me my bounce. But what that is, that's just this vector right here, right? From Q to the end of S if I start at P. So I want to look at this vector. And all that is S minus PQ. right, with the tip to tip. Or you can think of it as this way. If you have S going here, and then you did minus PQ, that would be like this. And so that S minus PQ would be this vector right here. Right? So once we have S minus PQ, we're pretty much there. Right? So in order to do that, I'm going to start at P, but my bounce vector, right, this thing right here, is just S plus S minus PQ. Right, so I'll get it over there. And so it's worth noting, if you have S plus S minus PQ, and this S is, again, a slide vector, so if I denote it with the arrow, that's just two S's minus PQ. Right? So that bounce vector is just 2S minus PQ. And again, if I actually want to get the bounce point, that's this thing right here, that's this blue dot. That's what I call the bounce point. I have to do a non-standard addition of a point, right, the collision point plus the bounce vector. So that gives me the actual terminal position of the ball after this one velocity step. So let's do an example. We have a ball that starts at 0, 0. So with our previous demonstration in mind, that was called M. Right? It wants to go to Q. It hits the wall at point P. I want to figure out a slide response and a bounce response. Right? And the nice thing about this is you can actually probably guess what those are anyway. If you're to take a wild guess, well, you're going to figure you're up here at 9, 8, 9, right? Just coming straight across from there. And I know I'm at x equals 8. And then if I wanted to guess what that point is, well, I just went over, how many points here? I went 4 over this way. I go another 4. Looks like I'd be at 4, 9. So those are my guesses. Right? But again, if you're having a machine do this, you can't really sit in there and tell it where this is going to happen. Right? Okay, so we'll see if our guesses are correct here. The first thing I need to do, right, if I want that slide vector, I have this projection of PQ onto W. So I certainly need P. And ask yourself, what is P? What is that point? I really need that point. Well, if you look at this line, the line that this vector sits on, right? And there's any number of ways to do this. If I just think of it in slope-intercept form, y equals mx plus b, I know that the intercept is 0. And the slope is just rise over run here. So the slope is just 9 over 12. And so that line is just y equals 9/12 x. And I'm worried about this point here. That's just on the line when x equals 8. So when x equals 8, I stick that into here. And I get y equals 9/12 8, which is just 6. So that point, the bounce point, or not the bounce point, but the collision point is 8, 6. 0.86. Right? And now I need this wall vector, but the wall vector is really easy to define in this case. It's just it's a vertical line, right? When you look at this wall, it looks like that, W, right? So that can be expressed as any vertical vector, 0, k. And you can have a 5, a 3, a 2, a 7. But if you want sort of a concrete way to figure this out, let's just take 2 points on that wall, right? There's this point, which is 8, 0. I know that's on there. And then I know there's also this other point, 8, 6. Right? So if I want my wall vector, I can just take my 8, 6 and subtract the 8, 0. And what I get in that case is 0, 6. So it should be a vector. But 0 anything will work, right? And so now that I've got my wall vector and my collision point, I just plug everything right into here. All right? PQ is just Q minus P, so that's 4, 3. And I need to dot that with W, which is just 0K, right? So if I take 4, 3 and dot it with 0K, right? Then I get 0 plus 3K down there. The size of W squared is just 0 plus K squared times W is just 0K. And I just left the K in there just so that it illustrates that it could be any number, right? And notice I'll get a 3K squared over K squared, so that'll just be a 3 here, and obviously the 0 stays. Right, so the slide vector, which is this, S is 0, 3. But to actually get the point, to get that point, I have to take my collision point, 8, 6, and I'm going to add the slide vector, which is 0, 3, and I'll express that as a point, which is 8, 9. And that is actually what we predicted, 8, 9. All right, so far so good. Now to get the bounce, I have to take 2s minus PQ. I have my s right there, so I have 2 of those. Minus PQ, I already figured out what that is. And so that's going to be negative 4. Let's see, that's 6 minus 3 is 3. So negative 4, 3. That's the bounce vector, which I call B. But to get the actual point, all right, the terminal point, that comes from taking P plus B, which is 8, 6, plus my bounce vector, negative 4, 3, which is just going to give me 4, 9, as I had predicted earlier. All right, so I can get my bounce and my slide, the actual bounce vector, slide vector, and then my bounce point and my slide point. No trig. That's the magic. Now in this case, you could have done it probably just by some geometry and reflecting things across lines. But it's not always that simple. These formulas here will work. And they will always work. And you can make them work in a machine. For example, suppose I did this entire problem in MATLAB. I first created this function called projection. And this is in the Chapter 2 program repository. And this is just a check to make sure that the lengths are the same. The two vectors, in order to project one vector onto the other, they have to have, they have to both be from R2 or R3. And so this is just that formula. By the way, this is the projection of U onto V. Remember, if you switch that order, you won't get the right answer. But it's just this thing. The dot product is an actual MATLAB function. Norm is an actual MATLAB function. It's just the norm or the length. And I square it. And I multiply standard multiplication times V. Right? And I'm going to use that in this slide bounce, which is also in the Chapter 2 program repository. There's where I start. This is where I hit. I figure that out by hand. And we'll show you different ways to do that in the machine. And actually, we did a little bit of that in Chapter 1. So you can automate that too as well. This was where it was supposed to end. I created the wall vector with these two wall points. Right? And so the wall vector was just the second wall point minus the first wall point, and that second wall point was just an arbitrary one. PQ is just Q minus P. So I have all of my parts. The slide vector is the projection of PQ onto W used from this function file up here. This is a function file. Right? You could have done it as an anonymous function within the program, but you don't really get to do the error checking with an anonymous function. And so once I have S, my bounce vector is easy to get. It's 2S minus PQ. And then my slide point, I just take my collision point, add my slide vector, which fortunately in MATLAB, they're both vectors of length 2. Make sure they're either both column vectors or both row vectors. And my bounce point is just the collision point plus my bounce vector. And this is just some graphic directives to do the plots. All right. And this was basically where it started and where it was going. That was the wall. This was the slide point. And so basically this first subplot 1, 2, 1, that's an array of plots, a 1 row by 2 column array of plots, the first one. So that's produced by this sequence of commands. And this bounce plot is produced by this sequence of commands. Right? And so this 19 basically just gives you that red line. This 20, that's the W, that gives you the black line. The slide point, it just gives you that red dot. All right. And then we did some labeling, some axis adjustment, and the same thing here, right? Okay, and there's actually a dashed line, a dashed line here that you can't see, but it's actually in there. It's between the point of intersection and the slide point. And the dashed line is visible here. But that's just some graphics. What you should do is, really, you should just grab this file, open it up, and run it. And then you can play around with it and adjust it for, I think there's a couple homework problems similar to this. All right, so that wraps up chapter 2.3, the dot product. Great operation, probably the most valuable operation you'll learn in this, possibly the entire book. All right, so I will see you in chapter 2.4.